today we are going to study something called law of large numbers and central limit theorem. These are parts of any formal study of probability theory, but these are essentially about repeated experiments. We generate what is called random sample. Suppose you want to study something about the population of some, population of the heights of the male members of a city. You cannot really go and check the height of each and every male member. So what you really draw is a random sample. So you really check the heights of certain number of male members of a city, and then using that information, that data, you come to certain conclusion about the actual or the average height of the male members of that city, or some more information about their heights. So this information that you gather is essentially by this process called random sampling. So you do not look at the whole population, but you look at certain members of the population. So taking a random sample is same as making a repeated experiment. So for example, when you are going to measure the height of people, so you are making a repeated experiment, you are measuring the height of person 1, then person 2, then person 3, and so on and so forth. So that is your experiment is the same. You are measuring height and you do not know what is the outcome, so that outcome is random, so that is a random experiment. So this lecture is going to talk about repeated random experiments. So to understand that, we will first begin with the notion of IID random variables. So what does IID mean? IID essentially means independently and identically distributed. So the IID is a short form of independently and identically distributed. So the formal definition is that if you have a sequence of random variables, could be a finite sequence, could be an infinite sequence, does not matter. If you have a sequence of random variables x1, x2, xn, then IID means that these are independent. So IID means that this means that these are independent. So these are all independent, and identically distributed means that distribution functions are same, they have the same functional format. IID random variables are the bread and butter of parametric estimation in statistics, and so on and so forth. This is the meaning of IID. So the key idea of these repeated experiments leads to the idea of sampling, or more precisely random sampling, if you want to be more erudite. So what do we do? Given a scenario omega, I am taking the value of the random variables, each one of them at omega. So I am creating the sample path So, these observations are numerical observations, these are real numbers, each of them are real numbers. This is real, this is real, and this is real. So, all are real numbers. So, these are observations, and if you take a finite number of them, then I say that I have taken a finite sample from the population. So, there are say 1500 people whose heights I have to know that this city has say 1500 people, and I want to know what is the average height of the people in the city. So, I do not go and measure 1500 people, that is a waste of time. The whole key idea of statistics is to do stuff by taking less observations and giving almost a nice answer. So, you want to measure the average height, you take a random sample. Of course, there is a whole study of how to take random samples. So, you take a random sample and then you look at the heights of those random samples and take an average of those guys, and that if the random sample is taken properly, then that would actually be a fairly good representation of the actual average height of the population. Of course, if you take a random sample quite large, then you will be giving much better approximation to the original actual random average height, which you would not know. So, this if you take say only finite number of them, then you are essentially doing random sampling. So, associated with this is first is the strong law of large numbers. You would ask me, is there anything called weak law of large numbers? There is something called weak law of large numbers, which will be a part of your exercise. So, here we are talking about strong law of large numbers. So, what does strong law of large numbers tell us? The strong law of large number tell us that if your random size of your random sample increases, then given a scenario omega, the average of the sample. So, if you take a finite number of samples, so suppose you have taken 500 samples, then you calculate the average height of those people, then if you keep on increasing, then this will be an approximation to the average height of the total population, but if you keep on increasing the number of people in the sample, then your sample average goes towards or tend towards the population average with probability 1, that is the idea. So, sample average tends towards the population average with probability 1. So, let me write down the strong law of large numbers. Let x1, x2, xn be a sequence of IID random variables. Okay. Random variables defined on the same probability space. So, because they are identically distributed, they have the same average, they have the same mean. Assume that they have some distribution. So, this is the once you take this, you are assuming that they have some density function and you can calculate the mean. So, you have to make this more simplifying assumption. So, that is say n. Then the probability that the sample average leads to the population average, which is m, is 1. That is limit, which is quite natural. It actually corroborates with our intuition. So, this is a very natural result. Of course, this simply means you are calculating this at every omega. So, given a scenario, so what is this event? So, it is a set of all omega such that whenever I take the limit of this as n tends to infinity, this becomes m. That set is a sure event. So, this probability, this event is the set of all omega in the sample space, set of small omega such that limit n tends to infinity x1 omega plus x2 omega plus dot dot xn omega by n is equal to m as n tends to infinity. Such a event is a sure event, and that is exactly what the theorem states. I do not want to prove the theorem right now unless I have time at the end. You can of course ask for the proof in the forum if you want, whether the proof can be given in the forum, but the proof is slightly involved. It is better to have at a first stage, many people would be possibly seeing this for the first time, and so it is better to have a clear idea what it says than just going into the technical proof. The technical proof here depend on two things. One is the Chebyshev inequality and one is the Borel-Cantelli lemma, which we had done in the last section and the last lecture. Now, once I do this, we have to move gradually to the notion of the strong law of large numbers. So, in order to do that, we introduce what is called the Bernoulli variables. The Bernoulli variables are random variables which takes either the value 1 or 0, means it denotes success or failure. So, if I toss a head, so if x is a random variable which denotes the number of head, then x of h is 1 and x of t is 0. That is, by success, if I mean that I have head, and if by failure I mean I have tail, then x of h, the random variable when evaluated at h should give me 1, and random variable which is evaluated at t should give me 0. Such a random variable which actually encodes success and failure, that is called a Bernoulli random variable. So, Bernoulli random variables are random variables that takes values either 0 or 1. So, for every point in the sample space, either at that point, when if you choose that point, it is considered as a success, will give you the value 1, or you will consider as a failure and give you the value 0. So, let x be a random variable which takes value 0 or 1. So, these are called Bernoulli random variables, right. Now, take a sequence of, so these are IID random variables which are Bernoulli, or IID Bernoulli random variables. And they either take value 0 or 1. So, for every I am given that if there is a success, the probability of success is P. If there is a failure, the probability of failure, which is 0, xi is 0, is Q, and P and Q both are greater than 0, and their sum is of course 1, the total probability, and any one of the two has happened, it will surely happen, either it is success or it is failure. P greater than 0, Q greater than 0, P plus Q is equal to 1. Okay. So, once I know this, I can of course compute its expectation and compute its variance. So, this will go as homework to you, we will not compute this, but we will write down the results. So, here we are now continuing from this part of the board and going up to this part. So, if you have IID Bernoulli variables, as stated, means as we have stated the probabilities of success and failure, then the expectation of the sum. So, this sum actually means how many successes I am having in a n repeated trials of the random experiment. How many are successes? So, if I toss a coin, toss head and tail, so say up to say 50 tosses, how many coins are actually head? Because for those the random variable will take the value 1. So, such variables which gives you the number of successes in a given number of trials, such variables are called binomial random variables. So, these x1, x2, xn are called binomial random variables. People who have studied binomial distribution would immediately catch this fact. So, this is called a binomial random variable. And the variance, because these are all independent, of course, I expect you to know this very basic way of calculating variances and expectations. As I have again repeatedly told you that this is not just a first course in probability theory, then we would not have reached this part within these few lectures. Because of independence, this is nothing but n p q, and those who know binomial distribution, they perfectly know that these are the mean and variances. So, we will now provide some sort of a limit theorem, which is called the Laplace de Moivre's theorem for Bernoulli random variables only. Once that is settled, we can that is one of the precursors to what is called the central limit theorem. This is sometimes also written as Sn. The sum up to n variables. So, I am removing the strong law of large numbers writing and write down the Laplace de Moivre's theorem, which we state for binary random variables, which could be actually better. So, this is also one form of central limit theorem. But starting with IID random variables which are Bernoulli. So, we consider x1, x2, xn as IID random variables, IID Bernoulli random variables. So, now we define the way we have defined Sn. So, I am just defining for the heck of it, otherwise we could have just picked it up from there. Then for any A and B, finite A and B, what you have is the following. So, here I am normalizing the binomial random variable by subtracting the mean and dividing by the square root of the variance, which is the standard deviation, which is called the standard deviation. So, whatever A and B you choose, this limit as n tends to infinity will always provide you the probability that a standard normal variable is lying between A and B, because here you see it is the density of the standard normal distribution standard normal density function. So, what does it mean? What is the conclusion from we can draw? The rough conclusion that comes in is that if you increase your number of experiments, repeated trials, as you increase the number of repeated trials, the Bernoulli and the normalized binomial variable, this is called the normalized binomial variable. The normalized binomial variable starts looking, or rather starts behaving like a standard normal variable, which is very important because binomial variables are discrete random variables, while that is a continuous random variable, standard normal distribution. So, there is a deep link between the two, and that is something which need to be seen. Now, this is the beauty that the limit theorems are connecting the discrete and the continuous random variables, and which is a very, very important thing. So, what are the interesting conclusions we can draw from the Laplace de Moivre theorem? We will actually later on modify the Laplace de Moivre theorem and write down the central limit theorem. The Laplace de Moivre theorem has the following. Suppose I have a scenario where my probability of success is half, just like a coin toss. So, this is basically the coin tossing scenario. Now, for any A greater than 0, it implies, using the Laplace de Moivre theorem, that limit n tends to infinity, probability of so NP, P is half, here you have root NPQ, which we have taken on this side, this has come 1/4. So, I have taken this here. So, we are basically looking at the whole thing between A and minus A. So, I would write it with one more step. So, basically it is this one. and this okay. Now this can be put in like this. So this can be written also as limit n tends to infinity p of minus a root n by 2 less than equal to Sn minus n by 2 less than equal to a root n by 2. This probability is in the limit is same as a standard normal variable lying between minus a and plus a. Now write down, take b to be strictly greater than 0, take b to be strictly greater than 0 and write a equal to 2b by root n. Then what I get from here is so what I get from here is that probability, of course there is a limit thing, I am not writing the limit, I am just writing in a very rough sense. This is very roughly so I am just plugging in a with this. So from here I get a is equal to 2b by root n, so I get this is almost similar. So there is a limit, so for very large n this is almost very good crude approximation of the probability, not very crude but alright, acceptable. So what does this show? As n tends to infinity, this goes to 0, this goes to 0, so they tend to 0. So as n tends to infinity, this whole thing is a bell shaped curve, it finally just becomes a line and then it goes to 0. This goes to 0. As n tends to infinity not equal to 0, this goes to 0. So essentially what I am telling that even though I know that the average Sn omega by 1 by n, so if I take the average, this goes to half in this case using the strong law of large numbers with probability 1, that is almost surely for omega almost surely. So means for every omega except a few, this goes to half. So probability of this event is equal to 1. That is what we get from a strong law of large number. But what we are seeing here is something very interesting. It says that you cannot bound this difference. The fact that Sn, this actually means probability, this one means probability of mod Sn minus n by 2 is less than equal to b, this is somehow going to 0, is decreasing. So the fact that you can bind Sn minus the binomial random variable, the deviation of the binomial random variable from its mean, that you can bind it within certain value, is that probability is less. So, it can fluctuate outside the value infinitely often or almost everywhere. That is, for almost every omega, Sn omega minus n by 2, this should be strictly bigger than b, which is a very so it can, so this can fluctuate with probability 1 above any value. This deviation can go above any value with probability 1. This is a very strange conclusion of the Laplace de Moivre theorem. Now we are going to remove the Laplace de Moivre theorem, the title, and end it with the central limit theorem. So what is the central limit theorem? Central limit theorem, which I write for short as CLT, considers IID random variables but does not consider a Bernoulli random variable. So you forget the Bernoulli. So you define Sn, which is no longer a binomial variable, just but a random variable which is a sum of n random variables, where E of xi is mu for all I, and the variance, because they are identically distributed, so they have same mean variance, we assume that they have mean variance. Of course, there could be random variables which are identical, which are distributed by some distribution, has some density but does not have a mean, like Cauchy distribution, but we are here assuming all those things. So it is sigma square. So then the CLT says that, and for any n's we have to replace this by mu and replace this by replace this not by mu, but if you have sum up, it will be n mu, and replace this by n sigma square. So it will be sigma root n. So this will be n mu sigma root n. So if you take any IID random variable, does not matter, and you take the sum and normalize it in this fashion in terms of the mean and variable. So n mu is the expectation of Sn, and the standard deviation of Sn is sigma root n, right. So if you take a random variable, subtract from it is the mean and divide by standard deviation, then when n becomes very large, that is the sample size is very large, it starts behaving like a standard normal distribution. So when you take large samples, you assume your population is behaving like a standard normal population. Thank you very much.